So digital clocks are more precise than analog ones because they first thing because both of them are accurate, but digital clocks are more precise, and by precision I mean that they can show the time up to the nearest microsecond or millisecond, or even in some of the high standard ones, they can even show time to up to nanoseconds. So that is precision. Precision is basically how much the two quantities that we have measured, they are close to one another. Let's just say we say that the time taken from for a runner to go from point A to point B is 12 seconds. Now, 12 seconds is a measurement, but if I use a digital uh, stopwatch to measure that time, it will show up to the nearest microsecond, and it will tell me that the time taken for the runner to run from point A to point B is not just 12 seconds, it is 12 seconds and 56 microseconds. So that is basically how digital clocks are better than analog clocks in terms of precision. However, when it comes to the price range, analog clocks are mostly cheaper than digital clocks. In competitive sports or in Olympics, um, very high precision digital clocks are used to time the runners or any athlete's performance. Moving forward. Now, another technique that we will be discussing right now is that whenever we are measuring a dimension, let it be time or distance or length or any other dimension, it is important to not just take one reading, but to take several readings. Getting more results in our pool basically decreases the chances of getting different kinds of random or human errors. By random error, I mean that every second the circumstances are essentially different. There can be less wind or more wind at one point, or if we're talking about um, distance from one point to the other point, the texture or the terrain of the area or the path that we are measuring can be different from one point or the other points. There are millions and millions of reasons that can contribute to random errors, and in order to prevent them and um, to normally distribute our readings, we take multiple readings in order to avoid random errors. Um, One of the most common example that is also given in a lot of questions, especially the practical ones, is that of a pendulum. A pendulum basically has let me try it over here. This point right over here, which is right under it's not under its position where it is attached, but let's just assume that it is, okay? So this is the mean point or the datum point. It is a neutral point. And when it goes over here or here, this is its highest point. And this over here, it's another higher point. So the time taken from this point to this point is one oscillation, or it is also fair to say that the time taken from this point, sorry, my bad, from this point is half oscillation. An oscillation is the time it covers to reach back to its original point. So when it comes back to this A point by going to B point and then coming back, that is one oscillation. But right now, this GIF over here that I have put, this GIF in itself is even slowed down or is played at a playback speed of 0.75, which means that it is uh, being represented slower than how actual pendulums work. So you can imagine that the time period of a pendulum is usually very, very, very small and even less than a second. Sometimes it's even less than a second. So for that, in order to find, if we are given a question that to find the time period of a pendulum accurately, there are two types of multiple readings that we are going to take to avoid random or human errors that could be caused during this experiment. The first thing is that instead of taking or timing it for one oscillation or one time period, we're going to time it for 10 time periods. So if let's just say I count it right now, like right now. If this is 1, 2, 3, like that. So instead of going for one oscillation, I'm going to time it for 10 oscillations or for multiple oscillations, right? So that is the first technique that we are going to use. Second thing is that I'm not just going to take one measurement of the 10 oscillations time period that it takes. I'm going to take multiple measurements of the time it takes to go about 10 oscillations. So the reasons I'm doing the first thing of taking 10 oscillations instead of one oscillation is that time period for one oscillation is really small. And when I start the timer over here and then I end the timer over here, when it comes back from here to here, it involves two chances of starting and ending in that very small time period when I can, as a human, add some human error by pressing the stopwatch or the timer earlier or later. So by giving it a time period of 10 um, oscillations instead of one oscillation, we're basically dividing that human error 10 times. Next thing, that why are we not just um, believing, or why is just not one reading of 10 oscillations reliable? Well, again, that is the same reason that we mentioned earlier, that in order to avoid random errors of different kinds, it is important to have as many number or repetitions of experiments when we are measuring something, because it basically reduces the chances of getting more deviations. So, for example, even when we are drawing a graph, let's just say I have a graph and this is a graph. Okay, this is just an axis. This is y-axis and this is x-axis. Okay, I'm conducting an experiment and I conduct 5 experiments. 1, 2, 3, 4, 5. And I'm supposed to draw a graph or to draw a conclusion from my experiment. There isn't a set pattern that I can see from these points over here, this one, or this one, or this one over here, that tells me if it will be a straight line or how would it actually be. What is the best fit line? However, when I start taking more um, readings, I'm going to see that there is actually a pattern. Like that some of the values are going to lie here, some of the values are going to lie here, some of the values are going to lie here, 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 here. And even some of them are not going to lie here because of very adverse conditions are here. These are basically the values. Now, the more the number of points, the more I can see that it's actually kind of a line or a straight line that is about between these points, right? And these other ones that are not really even close to lines, they can be considered as anomalies. That, you know, when we were taking B readings, there is some other kind of a very huge factor that, was different than the other readings that was changed in these anomalies. So we are not basically considering them in our test sample. Um, so for the pendulum, same goes for, I also put this picture over here from of random path from A to B, that if you're asked to measure the length of A to B, and it's just a very bumpy road, and like, from here to here, and then, somewhere from here, and then you come back to here like this. So that's a very bumpy road, and there isn't any chance that you can get the length right in one go. So you take multiple readings. Um, so we take multiple readings when we are measuring it, so that we avoid or we lessen the chances of getting any random errors.